So the talk is it's about symbol functions for symmetric frameworks. So what is it about? It's basically continuing a line of research that was initiated, I think, a little over 10 years ago by Steve Power in Lancaster. And it's about, I guess what the idea is to introduce methods from operator theory into rigidity theory. In particular, this is useful when you're looking at infinite frameworks, so say periodic frameworks that are quite popular with people. So it's a continuation of that line of research. Now, I'm going to try and present it in a fairly broad brush way. It's not a very combinatorial talk. It's very much focusing on the operator theory side. But I'll be sort of picking through it and trying to translate some of the ideas that are there into sort of rigidity theory language, I guess, if that makes sense. So I should acknowledge, of course, EPSRC for funding this project in particular before I do anything else, because I'll forget that. So hopefully you can see the slides there. If any issues arise, do let me know. So an outline here. I'm going to give you a little introduction with some nice, well, some pictures. I won't say they're nice pictures, but some pictures. And then I'll bring you through some of the theory, which is to do with intertwining relations. That will be a little bit more general than it doesn't simply consider rigidity context. So we'll get a bit more specific when we talk about symmetric frameworks, although it's still fairly general. And then there'll be a short bit about the RUM spectrum, rigid unit modes, and the RUM spectrum. And I'll kind of finish off with returning to some examples at the end. So let's see how that goes. Now, this is joint work with Eleftherios Kastis, who's one of the postdocs at Fields there at the moment, and also John McCarthy in Washington University in St. Louis. If you are interested in finding out more about any of this material, here's the paper to look at. This is a recently published paper here. Same title as the talk, and yeah, you can find that online now. Again, it's very much an analysis paper, hence the journal there, but hopefully it will be of interest to people here as well. So let's take a look. Okay. So just to get going, I thought I'd just present pictures just to spark some thoughts. So I guess some of you will be familiar with the sort of interplay between rigidity and symmetry. I mean, a lot of people have been looking at this over the last few years, but maybe you've been looking at it in slightly different contexts. So a lot of work has been done in the setting where you have a finite, let's say a bar joint framework, a finite bar joint framework, and you have, say, an abelian symmetry group there, and a lot of work has been done on that kind of a thing. I'm sort of almost reluctant to name names because there are so many people, and I'll leave someone out. But certainly, I've worked with Bernd and Tony on these kinds of topics lately, and things like that, and Shinichi and Tibor and people have done great work in this area, Victoria as well. So a lot of work has been done here, but what I wanted to do is maybe show you some pictures that maybe don't quite fit what has been done already, and maybe make us think about what we could be doing beyond that. So so that's one sort of side. I kind of think of this as two sides of a coin here. We have the finite frameworks with a finite abelian symmetry group as sort of one side, and then on the other side you have periodic frameworks that are infinite things with translational symmetry. And that has also been looked at by quite a few people, the periodic setting. And again, there's similarities between the two, but as far as I could see anyway, there's no sort of encapsulating theory to kind of capture what's going on in these different symmetric settings. So that's kind of what this paper is about, is trying to capture both of those settings in a single unified way, but also to extend what's going on so that we can look at new types of examples too. So so our first picture here, it's think of this as a bar joint framework in three-dimensional Euclidean space. We've been calling this the double helix framework for maybe obvious reasons there. Now, it's a symmetric framework, but the type of symmetry, it's, well, the symmetry group, the underlying symmetry group is Z, it's the integers, and the symmetry itself is screw axis symmetry. So it has this sort of screw axis thing happening. So it's neither a finite framework nor is it a periodic framework. It doesn't kind of fit into those two categories. But still, it's sort of similar. I mean, it's what you'd imagine that we should be able to deal with such a thing. So this is one of the kinds of situations that would fit in to what we're doing in the paper, this paper I mentioned. So I will come back to these examples at the end, but just to kind of introduce them just initially. So there's a Euclidean three-dimensional bar joint framework with screw axis symmetry. So you have a symmetry group. The abstract group there is the integers. It's just Z. What can we do with that symmetry? How does it interact with the rigidity matrix of our framework? Let's see. Here's another picture. It's again, they're quite simple examples. So this is a sort of, we call this the diamond lattice framework. It's just a two-way periodic framework with this crisscross pattern in it. So again, well, what is the symmetry we're seeing here? We have translational symmetry this time. So you can see that it's periodic in one direction. But we also have a reflectional symmetry here. Which you can see the kind of line of symmetry coming across the middle here. So we have a mirror there. So it's more than periodic, and but it's not a finite, and it's definitely not a finite symmetric framework. So there's another just simple context. Maybe it's too simple. So just for sort of just to make it a bit more exotic, you could say, well, maybe this isn't a bar joint framework, maybe it's something else. So I've said here, think of that as a direction length framework, just for fun, I suppose. So that means that the linear constraints, we're now thinking of them in different ways. So here, the black bars are supposed to represent distance constraints, and the red bars are supposed to represent directional constraints. So can we deal with that situation? You know, it's a framework of some particular type. It's got a symmetry group there. How does that interact with the rigidity matrix in this particular situation? Okay, so that's example number 2. And the third example, it's just a finite bar joint framework. Nothing too complicated here, but we could think of it as we could change those distance constraints. So that's what I want you to think about here. So you imagine you took this bar joint framework. It lives in 3 dimensions. It's a 3-dimensional framework. And so first of all, what kind of symmetry has it got? It's got a 4-fold rotational symmetry. It's also got a reflectional symmetry in there. So that I mean, we could take a nice finite abelian group there and say, okay, we have theory that we can apply to that already. But what if you change the distance constraints? So what if you said, this is Sean would have been saying lots about this, no doubt. So what if you change the distance constraints in some way? Can we still talk about the interplay between rigidity and symmetry? Have we the tools to do that? So there's 3 examples, just to keep in mind as we go through it. What I'll do now is I'll go on to, I'm going to give you a summary of one of the main results in the paper, and I want to talk through the bits and pieces that are in it. So this is a picture that you'll see in the paper, and what it is basically describing a factorization for the rigidity matrix in a more general setting, but essentially we can think of it, you know, that's what's going on here. And it captures both the periodic situation where you have a periodic bar joint framework, say. It also captures the finite symmetric, finite abelian group setting, where you have a bar joint framework with a finite abelian symmetry group. And it's general enough that you can vary the types of constraints that are there. It doesn't necessarily have to be Euclidean distance constraints for every bar. You can mix things up a little bit if you want. So I want to try and talk through it a little bit just before we go on. So the key, so the main linear map that we're interested in is the guy up here, this guy, which you can just think of that as the rigidity matrix. So just you might as well pretend that's a rigidity matrix right there. The notation is because we're working in a more general setting, and we don't necessarily want to always presume it's a rigidity matrix. There could be other contexts where this will be useful. So this is called a co-boundary operator in our paper. Co-boundary operator. So C for co-boundary. And the only reason for the title co-boundary is that you'll see that it's mapping from some sort of space involving a set of vertices. You can see a vertex set in here into a space that involves some set of edges, and you can see a set of edges over that side. So anyway, in an application, that's probably going to be a rigidity matrix, let's say, for us, and we can just make that assumption there. Now the phi there, usually you have GP when you talk about a bar joint framework, say, so G and a P. So the phi there is again just capturing the idea that we don't necessarily need P. If we can talk about more general types of linear constraint, and it's not always necessary to have a set of points in a space. You can just have a graph and some linear constraints attached to the edges, whatever is relevant to you, you can use. So that's what the phi is. It basically is a collection of linear constraints rather than specifying points in a space, which is a bit more specific than we need. Okay, so maybe you're familiar with this notation, but I'll mention it anyway. This is little L2. These are the square summable sequences of, these are X values. So I should underline what I'm talking about. So on this side, little L2 of Vx, think of these as sequences of vectors in a space X, this capital X here, which are square summable. So maybe the easy case to think of would be, okay, let's say you have a bar joint framework. You want to assign velocity vectors to all the joints in that framework. And if you have an infinite framework, then it makes sense to restrict your attention to assignments that are not too big in some sense. So let's restrict our attention to square summable assignments of velocity vectors to our infinite framework. So that's what's going on there. So if your bar joint framework lives in R2, let's say this X here is probably going to be C2. The complexifications of C2 here would be your space X. So you could put in C2 there if you like. Over on this side, similar story. So on the other side, we have square summable sequences. But again, well, we'll think of these as sequences in Y. This is probably just going to be the complex plane for us. Okay, if you think about the rigidity matrix, so you're mapping, so you've got your columns indexed by vertices and coordinates, and you're mapping into where you're mapping into a space indexed by edges. So that's pretty much what we've got here. A space, a sort of vector valued space indexed by vertices into a vector valued space indexed by edges here. We might as well take C on this side over here in our application for rigidity. So that's something you'll see only in an infinite setting. This is sort of L2 context. We don't need L2, of course, when we're dealing with finite frameworks. But if it's a periodic framework or something else, we do need to, for what we want to do, we do need to restrict our attention to a nice space of velocity vectors, if you want to think of them like that. So that's what's going on in the top row there. Now, in the presence of some symmetry, so gamma here, you'll see a gamma in here, that's our symmetry group. So that's the symmetry group for your framework. If we have a nice symmetry group and everything is sort of nicely laid out, we can identify this our original L2 space with this other L2 space from the group, the symmetry group into a space where, I mean, it's quite a natural identification. We're basically, what would be a simple example? I guess if you're going to take your group to be Z or something, so you could imagine this is Z if you just want a one-way periodic thing. All we want to do is think about our velocity vectors as what we get when we assign velocity vectors to vertex orbits and then shift those around using our integers, say, back and forth. So that's what's going on there, just a little identification. So that's not a very deep thing going on there. Similarly, on the other side, we're going in the reverse direction, but again, it's just a simple identification between those two L2 spaces. So we can do that when we have a nice symmetry group gamma, say. And then the next little maps that you see are Fourier transforms. Okay, so here on the left-hand side, we have a Fourier transform from little L2 into a Lebesgue space here. This is big L2, and this is the dual group in here. This is the dual group gamma hat. So in the case where gamma is the integers like we had here, gamma hat would be a circle. Okay, so this would be square summable, or sorry, not square summable, square integrable functions on the circle. And again, vector values like we have in here. So this is a Fourier transform, this F, and similarly over here we have an inverse Fourier transform. Now I skipped over this guy. This is another. It's again, all of these are Hilbert spaces. All of these spaces we're looking at, and all of these maps, other than the co-boundary operator, well, SV and the Fourier transforms and SE and this T over here, these are all unitary transformations of our Hilbert spaces. So so this T is coming about from the symmetry of the framework. It depends on some little unitary representation here, tau tilde here, that pops in, that arises from the symmetry of the framework. So that's a little unitary operator there. Now, if you were doing if you had a periodic framework, this map here, this T, you wouldn't see it. It wouldn't be there basically. We refer to this as a twist in the paper, and we don't have a twist when we just have translational symmetry. But if we have some other sort of symmetry operations in there, then they will have a linear part to them. So if I give you an isometry, it will have a linear part and a translational part, and the linear part is giving rise to this little twist that we need in here. So that's a sort of overview of that kind of factorization. So what we're saying is that with a symmetric framework, with say an abelian symmetry group, our rigidity matrix up here can factor through all of these maps. And in particular, you'll see that there's a map down here, which is, this is a multiplication operator. So M for multiplication, and this little phi down here, this little phi that you can see here, that's the symbol function. So the title at the top, that's the thing that we're interested in. Okay, so we want to sort of explain why there's such a factorization, and what exactly that symbol function is for a given framework. Now, a bit of a spoiler. The symbol function, if you've worked in the area, your orbit matrices, and that symbol function, essentially, these are the orbit matrices that you're familiar with, right? So it's going to be a function defined on the dual group, whatever that might be, and it's a function defined on the dual group, and for every element of the dual group, it's going to give you a corresponding orbit matrix. So that's what it is. So what we're doing is capturing all of that in a nice general setting that can be applied in different lots of different cases. So I'll run through some intertwining relations, but I don't want to spend too long on technicalities. I refer you to the paper because it's too short a time, I think, to get into. But anyway, the starting point is that we have a locally compact Hausdorff abelian group. in practice, this will be a discrete abelian group. If you want to think of it as a finite abelian group, that's fine, or Z or something like that. If you like periodic things, or Z2 or something, you can think of it like that. That's fine. The way we present this in the paper is we start off with the scalar version of our what's called an intertwining theorem. We start off with the scalar version of that, build it up to a vector valued one, and then add in the twist that we need to make this work for rigidity matrices and other types that are similar. So you can see here we've got, in the scalar case, just the regular square integrable functions L2. And for such a space, for each element of our group, we have what you can think of here as a sort of shift operator here, so a sort of shifting that happens coming from each element of our symmetry group there. So this is all scalar valued stuff. And what you'll see in this proposition is a statement that says, if you have an operator, which is called L here, on your space of square integrable functions, and well, then the following are equivalent. You have an intertwining with these sort of shifts, if and only if your operator is unitarily equivalent to a multiplication operator. And that symbol in this case is a function. It's an essentially bounded function on the dual group. So this is kind of classical stuff. This is well-known stuff. Moreover, the unitary equivalence is coming about using Fourier transforms. So the F's there are the Fourier transforms that are available. Now that's not good enough for rigidity matrices. Okay, so we don't have scalar valued. We're not in scalar valued context there. So we have to soup it up a little bit. So we turn it into a vector valued theorem. Okay, so we introduce complex Hilbert spaces and make everything vector valued. And we have to do the same with those shift things. We have to make them vector valued, so we replace them. And we also notice that rigidity matrices map from one type of space into a different space. It's not from the space into itself. So there's a subtle, there's a difference there. That's why we have two different Hilbert spaces, X and Y. So we can go from L2 gamma X, say, into L2 gamma Y. So one type of space, a vertex space into an edge space, two different things. So we do that, we make things vector valued, and with a bit of work, we get a corresponding theorem here, a vector valued theorem. Again, what we're saying is that we have intertwining relations if and only we have a unitary equivalence with a multiplication operator. The symbol in this context is a little bit more complicated than that. It's not a scalar valued function. It takes values that are linear maps from or bounded operators from X to Y. Okay, so for each element of the dual group, phi of that element is an operator from X to Y. But that's still not good enough because the rigidity matrix needs an extra twist. So we have to introduce that next. So where that comes from, or what it looks like, is essentially a unitary representation. So we have a unitary representation here with which we can define a unitary operator on our vector valued L2 space. And then in addition to that, we have to take our vector valued kind of shift here, this guy, and we add a twist to that as well. So the U lambdas now have a U lambda pi, so an extra twist to them. So we're just adding in machinery that we need to capture rigidity matrices, what happens in that context. So doing all that, we get a similar theorem. We get an intertwining property if and only if our operator, whatever we call it, is, in this case, it's product of something that is unitarily equivalent to a multiplication, and or it's a composition, I should say, and a unitary operator T pi, which is the coming from the twist. Okay, so that's sort of the first step of the paper, is to establish that we have such a multiplication operator and such a symbol function phi here. So the next thing is to kind of start applying that to frameworks and thinking about what this symbol is, and then also what is it good for as well, another good question. So again, I won't spend too long on the subtle details, but I'll try and introduce what happens next in the paper at least. So When we talk about a framework, we don't necessarily mean a bar joint framework. We just mean a pair where we have a graph and then we have a collection of linear constraints that satisfy just enough to make everything work out. So in particular, phi is a collection of linear maps from our space X to Y, which satisfy this kind of little property. So you can think of this as the linear map where you take the dot product with PV minus PW, and that's the standard Euclidean setting, but it needn't be that. A co-boundary matrix is just a more abstract rigidity matrix. It has the same structure. We just plug in, instead of our PV minus PW, we plug in our linear constraints or linear functionals here. So for example, if I gave you a Fourier cycle, you could write down a nice co-boundary matrix. We're not specifying points P in space, we're just specifying linear functionals in the entries there, and that's what it would look like. Okay, so then we introduce symmetry, and so to do that, we introduce our abelian, or it's going to be a discrete abelian group in this context. And so first of all, this is kind of the usual approach if you've worked in this before. We have a gamma symmetric graph, and then we have a gamma symmetric framework. So we have a group action in both cases, and importantly, we have this special link between the constraints. So if I were to, so tau of our group element here is think of that as my symmetry. If I apply that and then apply my linear constraint, that's the linear constraint I get from this sort of image of an edge that's happening. So it's a familiar sort of condition, just in this slightly more general setting. So anyway, the point is we introduce symmetric frameworks, and then we can prove using our intertwining results that we have this factorization, the factorization that I showed you at the start, essentially, which if you write it out, it looks like this long-winded thing here. So the question really is, what is phi? What can we say about that? So I'll try and say something about that in a couple of minutes. So if I were to take an element, so step one is to introduce orbit matrices. You might be familiar with orbit matrices. Now, maybe you've used orbit matrices just for the sort of fully symmetric sort of problem where you just you take a single orbit matrix and work with that to characterize fully symmetric rigidity or whatever. But there's also, say if you're in the finite abelian setting, there's going to be other orbit matrices. You're going to have a collection of orbit matrices, one for each character in your group, dual group, say. So that's what we're trying to do here. We take an element of the dual group. So remember, gamma here could be an infinite group, it could be a finite group. It's a discrete abelian group. That's the important thing. We have a chi-orbit matrix, which is defined in this very general way. So notice we haven't specified very much about the framework, just that we have linear constraints and we have a group action. So we haven't made huge assumptions at all. So we just defined what the row entries are going to be. This orbit matrix, so the rows are indexed by edge orbits, the columns are indexed by vertex orbits. And here's a little example, just to see. I just gave you a graph here with a natural sort of symmetry in it. And this is called a gain graph. I'm not going to define those, but this is something that you do work with in the setting. And using this information, you can construct orbit matrices. Again, I haven't specified the geometric information at all. I've just said, let's suppose we have a framework with some linear constraints, and this is what the orbit matrices should look like. So then we are able to show that the symbol function, the thing that we introduced earlier, which was an essentially bounded function from the dual group into this space. These are the bounded operators from, well, our space X. These are the vertex orbits up here, V0, these are the edge orbits up here. So our symbol function, well, the values it takes are exactly these orbit matrices. So think of it that way. So when I evaluate my symbol function at a character, I get an orbit matrix. And that's the key idea there. So that connects those things. I don't have much time. I'll fire through some examples quickly. So here is just a corollary that is just basically pointing out that if you had a finite abelian group, this all collapses down into the well-known block decomposition. of the rigidity matrix into orbit matrices. So that would be a special case of what's going on here. So the picture I had at the start, that all just kind of collapses down. You just have a multiplication operator where the symbol function is a function on a finite set of characters, and it all collapses down to that. It also allows you to think of the symbol function in other ways. So you can think of it as a trigonometric polynomial with this sort of a formula, and you can write down the Fourier coefficients explicitly there using your rigidity matrix and the twists that are happening in your symmetry. So you can do all of these nice things. So maybe it offers a new perspective on orbit matrices if you like using those things. So one other thing that we do in the paper is we think about rigid unit modes. So that these are things that are studied in the setting periodic frameworks, and they certainly appeared in papers of Steve Parrott. He studied this a lot. What we've done is generalize the idea. So all you need is a character, and then you need to pick a vector, sort of assignment of velocity vectors to the vertex orbits. You can construct a bounded vector. You can think of it as a sort of assignment of velocity vectors to the joints in your framework with the property that the L infinity norm is bounded, is finite. So then down here, we're just saying that these special kinds of velocity vectors, we're going to call them chi-symmetric vectors. And what we can say is that if you picked something, say a vector A in the kernel of this is an orbit matrix, phi of chi, then you can construct one of these chi-symmetric vectors, and this will be an infinitesimal flex. It will be in the kernel of your rigidity matrix. So these are sort of an interesting class of flexes, and we get a generalized rigid unit mode spectrum out of that, which is defined as a subset of the dual group. So it's a more general version of what has been there before. So just to wrap up, if I can manage in 2 minutes, hopefully that's okay. So the three examples I showed you at the start, I gave you a sort of double helix thing with screw symmetry. We worked through this in the paper, and we worked out a symbol function for that. We worked out the RUM spectrum is the entire dual group, so it's all of the circle. And we worked out some of these chi-symmetric infinitesimal flexes explicitly here. So you can read more about that in the paper. I'll show you the direction length framework. So this is the one-way periodic framework where we changed some of the constraints to directional constraints. Again, we're able to work out a symbol function in that context. The symmetry here was translational in one direction, and we also have mirror symmetry in the framework. So the group there is Z times Z2. So our dual group is the circle times Z2. And we get a RUM spectrum. It's not the whole dual group, it's a subset of the dual group. And then we worked out some infinitesimal flexes in that context, some of these bounded chi-symmetric flexes. And then the last example, just to finish, that was the thing with rotation, fourfold rotational symmetry, and had a mirror plane in there as well. So I said, think of that as a framework, but maybe change the distance constraints to see if you can do that. So in the paper, we imagine that we're using these distance constraints. So we specify this particular norm, and we work with that. And again, we just work out a symbol function. We work out the RUM spectrum. So for which characters chi do we get these bounded chi-symmetric flexes? And we worked out some of these chi-symmetric flexes here explicitly as well. So anyway, I'm out of time, so I better wrap it up there. So I will just say thank you very much, and I'll leave it there. Thank you.
Thank you, Derek. Fascinating. I always wanted to know about the RUM spectrum. Are there any comments, questions?
I have a question. So I want to understand this assumption you make at the very beginning where things are like square summable, so you can, so things actually work. So does this create an obstacle if you're dealing with, say, like, periodic frameworks? Like, I guess like the example I have in my head right now is, say you have something with like in Z2, say with lattice symmetry, and you're dealing with a fixed lattice. If you just like, rotate and you have a bunch of like disjoint squares, say at like every lattice point, and your motion of this is just like you rotate each square or something. It seems like those velocities aren't square summable, but I feel like I might be missing something.
I'm not sure I understand, but are the velocity vectors getting bigger as you move out from the origin?
No, they're the same at all places.
Oh, they're the same. It sounds like they're bounded, but not L2. Yeah.
Okay, so this would not. So I guess you would need to have like a flexible lattice or something for this to where they're getting smaller, or
that I don't.
or what?
I'm not sure.
Sorry, that didn't make sense.
I mean, you need the velocity vectors to decay. Yeah, so they have to tend to zero as you move out somehow. Yeah.
Okay. Nice.
Derek, I think that the way that we find afterwards the velocity vectors are actually through a kernel, so we can find the periodic vectors. The way that we define the function, it is bounded in order to use the Fourier transform, but then we work with approximate identities in order to find the periodic vectors.
Yes, yeah. So these chi-symmetric flexes are not L2. They are bounded, but they're not L2. So those ones we can find. Yeah, as Eleftherios is saying, we restrict to L2 initially, so that we can introduce the Fourier transform basically, and we need that there. That's the reason that we introduce it. But once we have it, then we get the symbol function. Once we have the symbol function, we can construct the bounded flexes, not necessarily L2, but bounded.
Okay. Thanks.
So with the RUMs spectrum, you have, I think it's a result, Steve, where the existence of a finitely supported flex is the same as the existence of a square summable flex. Is that always going to be the same here?
Actually, we didn't look at that problem. That's a good one to look at next, actually. So certainly true in the periodic case. So Steve has written on this, yeah. I would guess it is, but without having tried it, maybe I should, yeah, I won't say for definite whether it is or not, obviously, but it seems reasonable that it's worth looking for, yeah.